Okay. I guess everything is fine. Let's get started for today's session. Where are we today? So today we are going to look at fan of flows. Welcome all to the live interaction session, uh, session 9 for this NPTEL course series on gas dynamics. You have been looking at video lectures from Professor Shisha Rao, and I have been taking live interaction sessions. I'm a Prime Minister Research Fellow teaching assistant for this course. I am Shrey Sahai Gupta. I am a doctoral student at IISc Bangalore, and today we're gonna look at something on Fano flows. So let's just get started with that. Just give me a second. Right. So let me get started with this. I have given my introduction several times previously, but in case you have been you're looking at the first video recorded session of this session, recorded version of this session. I am Shrey. I am originally from UP, Uttar Pradesh, from the city of Agra. I did my bachelor's from IIT Roper. Um, then I working in industry for roughly a year. Joined my doctoral degree, and currently I'm in my fourth year of my doctoral degree. Um, Here are my some contact details. You can visit my website or LinkedIn if you would like to connect with me or discuss problems beyond these sessions. That is very much welcome. Let's go ahead. Um, let's do a recap. So the last session we did was on variable area flows. And in fact, the last two sessions were on the same thing. In the last session, we looked at the application part of it. The application of variable area flows is profound. In fact, any wind tunnel design, supersonic wind tunnel design, involves this variable area flow analysis. And in that context, when you're accelerating flows from stagnation receiver or reservoir, you need a nozzle to accelerate the flow to your test section, and accordingly you design things. Um, in that regards, we saw that normal shock is the baseline diffuser. Uh, Diffuser is an contrary to a nozzle. Normal shock is a baseline diffuser which increases pressure across it, and depending on how where is the location of a normal shock in a nozzle, it gets defined as either it is uh, overexpanded or underexpanded. Uh, Generally, if the nozzle is subsonic, your Mach number remains well below 1, and in the first critical conditions, your nozzle throat conditions become sonic. If you intend to accelerate the flow further beyond the throat, um, then what you need to do is decrease the back pressure or increase the reservoir pressure. Um, and accordingly, you will get supersonic flow in the diverging portion of the nozzle. But depending on the pressure ratio you attain, you will not just simply get supersonic flow in the entirety of the diverging section. You'll get supersonic flow in only a part of it, depending on the pressure ratio. So it turns out that if your pressure ratio is not high enough, or your back pressure is not low enough, then portion of the diverging nozzle will be subsonic, where your pressure will continuously um, I guess increase. Let me think about it. So your flow, your behind the normal shock, you will be decelerating the flow because of the diverging section, and your static pressure will increase. Right. But you can move this normal shock towards the end of the nozzle by decreasing the back pressure so that the required compression behind the normal shock is also lower, and so that this normal shock can move towards the exit of the nozzle. In the case when the shock sits at the nozzle exit is called second critical conditions, where the normal shock directly compresses the compresses uh, so entirety of the nozzle is supersonic, but because now you need the flow to get decelerated back to the ambient conditions or back pressure conditions, the this normal shock will do the job for you. It will decrease the flow to subsonic conditions, and then the subsonic conditions will go isentropically to uh, stagnation conditions, back stagnation conditions. Um, Again, there will be a drop in the total pressure ratio behind the normal shock, uh, and you will see you will start to see oblique shocks appear. So this is the strong shock solution, where the normal shock directly um, implies a very low Mach number. But if your back pressure is a little bit lower, you will see that there will be some oblique shocks rather than normal shocks. In the third critical conditions, there are no shocks or anything. You simply very smoothly, you have chosen your back pressure nicely. Your design has been nice so that you don't expect any shocks, and your flow at the exit of the nozzle is supersonic. Whatever is going to happen behind this exit of the nozzle is a different thing, but at least there is nothing there in the entirety of the nozzle. If your back pressure goes even below, then you will experience uh, uh, expansion waves, which will decrease the pressure further from the nozzle exit to the static or the back pressure. So you require some Prandtl-Meyer expansion fans to do the job. Okay. Um, Let me now move to the other part of it. So today we are going to look at fan of flow, and I thought it would be nice to first look at what is going on in fan of flow. So fan of flow, what you will see soon as the three effects which we've been studying in these one-dimensional flows or quasi one-dimensional flows. The three cases are variable area flow, uh, then there's fan of flow, 1D flow with friction, and then there will be also 1D flow with heat, which will be called Rayleigh flow. You will see certain similarities between all these three conditions. In fact, you can also compare normal shocks in this category, because a static normal shock is also a certain 1D supersonic flow setup. So we'll see that there will be certain similarities between all these features, and we'll talk about it. And essentially, the similarity is arising from the commonality between the three governing equations. So in different cases, in different what do you call it, surgical this um, what is that word? So in each case, in each scenario, you see some out of these three governing equations, one will change its form. So in variable area, rho u is not constant; it's rho u a. So additional area variable also comes in the place. In fan of flow, you see friction factor play a role. Um, so friction factor plays a role in fan of flow. Let me just admit someone. Sure. switch the screen back. Today. So, yes, great. So let's continue what I was saying. So you see that in different cases, either one or more equations. In the form, so enters the picture, and similar effects are going to be seen. Again, in both the flows, total enthalpy remains constant. Um, one person I have to admit. Great. Um, guys, do you have any questions for this session, or should I continue with my whatever I have prepared?
No, sir, not from my side.
Okay. Now, okay, I also thought that I also was not able to find this discussion on Fano flow in that Anderson book. So let me just share the books which you can use to go through these chapters. Sorry, go through these topics. My laptop is a little slow today, so bear with me. It will be a little, will take some time to show. So let me share my screen, show you the books. So I'll stop sharing this. Pretty slow today. One of my code is running, that's why. You're able to see the screen. No, this system is not responding
No,
well. You're not able to see my
not.
screen.
I can
Okay,
see the PPT, no
you can see
flow
the PPT.
constantly.
Okay, okay, okay. Let me stop
Yeah.
sharing that. Why is it not? Uh, Acha, meanwhile, it is not responding. How are the video lectures? Did you go through them?
Yes, sir, I did.
You felt
They
any,
were good. Yeah.
yeah, you were able to follow, right?
Yes, yes, sir.
Of this code, then. It behave like this, I can't. Let me check. I was thinking, or maybe I'll just show that to you. What is happening? Let me see. Now it will work. Let me check. Hmm, Probably now everything will be fine. Fine. Hmm, Let me stop sharing this. I'll share the books. Stop sharing. Just go. What is not this? PowerPoint is now so fine. Let me close a few things. You're able to hear me?
Yes, sir.
Able to see me? Everything is fine. What is going wrong then? Hear me? Okay, fine. Let me go this stuff. Or tip to everything is we open task manager first. Okay. Let me try this. Fine. Let's see. Able to see my screen. This is also okay. Okay, fine. This one also okay. Okay, you're not able to see the screen. Okay, now it would be okay. So
Yes.
the first book is Zucker. So the first book is this Zucker, Gas Dynamics, Fundamentals of Gas Dynamics. That is the first book. Please let me know if you don't have a soft copy. I might be able to help you out with that. But then the other book, this is a nice book in itself, but you might also want to look at uh, this other one. Additional. Yeah, Gas Dynamics by Zucro, I guess. Yeah, yes. So Morris J. Zucro is the second book. You can look at it. Let's see how is this given. So part of it is also what we're going to discuss. So I think 243. You can go through this book as well if you would like. I think Anderson does not have these book chapters as standalone chapter. So what about Anderson? Let's see. So their first chapter is this one-dimensional flows. Yeah, so they have only two sections of this sort. Let's see how these sections are. I have not gone through these sections. Mm, 102. So they have derived things. Okay. This is the sonic reference conditions, star conditions. This is Rayleigh curve. Fine. Rayleigh, we are not going to discuss today. Okay. This is the fine. Great. Okay. Uh, Yeah. So only a brief discussion, good enough in itself, but maybe let me stop sharing now. Let me discuss. I thought let's try to plot the Fano curve ourselves today. That could be a good illustrative exercise instead of just solving some problems. I thought that would be a good change of pace. So let me see. Okay, before that, yeah, let me go back to screen. Yes. So before that, let's do this small problem. Now that you are there in the chat, would you like to solve this? Straightforward, nothing much. But do you want to try? These are six potential Fano curves. We need to identify which one is the correct one. I think this is
Oh,
one of questions from
I
the
think
assignment.
yeah, it's I think the bottom left
This one,
most.
bottom left,
Yeah.
this one. So
No, no,
P1 is greater. Okay. No,
no.
not this one.
No, no, bottom left, bottom left.
What this one, right?
No, no, left, left, not the
Oh,
right one.
left. Sorry, this is right. Okay. This one.
Yeah,
This
bottom left.
one. P1 is greater than P2 is greater than P3. G1 is greater than G2 is greater
The,
than 3.
yeah,
Okay.
actually, this is the only difference is that it's the only one having subsonic branch above everything. In
Okay. So
all,
one thing. Okay. Good. Good. That is what I wanted to do with this example. This is a good one. Let me just try it. So only one with subsonic. You're able to see, right? What I'm writing above
yeah, yeah.
supersonic. Think you're able to see. Let's see. So this is one point. This because this is supersonic is above subsonic, so no, again no, and all of these, right? Fine. If we forget about that, let's see what are the other reasons A is not a correct Fano curve. So one is this, which I've written down. What are the other things which are wrong in this first graph? P1 is greater than P2 is greater than P3 is fine. G1, right? So can we see why a higher, so why with a higher flow mass velocity, this curves goes leftwards, yes, not rightwards. Do we know why? Why do we know that this G1 is greater than G2 is greater than G3? Wanna guess? So the other thing is, let me just write them down. Shift with increase in G. Okay. Uh, then would you like to also answer? See, in one of these, P3 is greater than P2 is greater than P1. This one. can this isobar be greater than this isobar can be lower
No,
than this isobar?
no,
How
no,
do
no.
we know that with increasing isobars,
Because
with increasing pressure, isobar goes up? Why?
it's
On
because
a
if we see if we consider one Fano curve, so from
hmm,
when we go from left to right in the subsonic
hmm,
region, the velocity, the Mach number goes on increasing as we go from left to right in the subsonic region.
yes,
And in the,
yes.
so initially the pressure is high enough, but then as the Mach number goes on increasing, the pressure drops.
You're
So
saying
we see
pressure,
as
uh, static
from
pressure drops, right?
yeah, the pressure
So,
goes on decreasing. So
okay.
from left
What
to right,
about? Hmm, okay. Okay. So the logic is that along a Fano curve, static pressure drops. That is the logic of dismissing this trend, right?
yes,
Right? Okay. What if I had not given you a Fano curve in the first place? What if, let me do that. What if, see, your reasoning is more than appropriate. In fact, it is it's good, but just a speculation. What if, okay, first of all, before that, what are these curves called? Not very important. For the, just like that. Do you know what are the name of this HS diagram? We call them Molliers diagram. You might remember it
oh
from
yeah, yes, yes,
thermodynamics,
smaller,
right?
yes.
Yeah. So anyways, on a HS diagram, uh, what if these are three isobars, or let's say two? We know P1 and P2. Can we say anything just by looking at the isobars in the first place? Do we know which is, now that you know that P1 has to be greater than P2, but can we just say that out without using the reference to Fano, without referring to Fano curves?
We
So,
can actually
hmm,
like
yeah,
so
TD. Hmm.
uh enthalpy is a function of pressure and temperature.
LP is a function of pressure and
Mm, We
temperature.
we so at if we say uh,
Huh.
we say that yeah TDS is pH minus VDP. So at a
Look what
certain
happens
point,
along an isobar. Isentrope.
yeah,
Along an isentrope,
isentrope. So
what is going
DS
on?
becomes zero. Yeah,
Yes.
DH is equal to VDP, which is what CPDT equals
We don't need to do
VDP.
that. So, you're going on the right direction. Just to maybe just a thought. DH equals to VDP, right? Can we say
Yes.
anything about the polarity of V? Is V always positive? Can it be a negative number?
No, it can be. No, it cannot be.
It
Sorry. It
cannot
cannot.
be,
Sorry,
right?
it cannot be.
So,
Sorry.
if DH and DP will have the same polarity. If
Yes.
pressure increases, only then enthalpy can
Only
increase.
then enthalpy. Yes.
Simple, right? So that is
Yeah.
one thing. Okay, now let's go back. So this thing is sorted. So we know that how isobars, increasing pressure shifts the isobars upwards. So that is one thing. Maybe I'll not write that. So what about this? So this one is the supersonic branch. This is exactly same as this one. It's just supersonic branches on the top of the subsonic branch. Okay, this is fine. What about this one? G1 is greater than G2. P3. This one is the same isobar issue. Isobar issue. And what about this
Yes.
one? What about this one? And this is a stupid graph. So isobars.
Cannot.
Okay. Acha, what is wrong with this graph?
the bottom right most, right?
Yeah,
Uh, they have just what G1, G2, G3. Oh, okay, G1, G2 is not denoted to the Fano lines, the Molière curves. Oh, okay. They have just
yeah,
switched the naming.
yeah.
G and P.
So basically, if we have to put it technically, you can just say that the isobars do not look like Fano lines, and Fano lines do not look like an isobar. So they're you got it. Just that the shape in the itself is fundamentally wrong. Fano curves have to be like of this shape. They cannot be. They cannot intersect H naught. They have to be asymptotes to uh, asymptotes to H naught line. So the problem, and P1 and P2 are also cannot be so isobars can also be not asymptotes. They have to cross a constant enthalpy line. So that is fine. Now let's look at why subsonic branch is on top of supersonic branch. Do we know that? So we are going to discuss, like we are left with these two things. First of all, why subsonic branch is on top of supersonic branch, and why G shifts leftwards upon increasing. So the first one, let's address the first one. Why subsonic branches on the top?
So, at so if I consider an isentrope at a
Hmm.
certain location, so it will,
Isentrope.
yeah,
Isentrope.
yeah.
Yes.
So like that line uh, in such a way that it will cut the curve at 2 points.
Two places. Yes.
Yeah. So I would get 2 points. So what can I say about these 2 points is that that the point on the top would have higher
Hmm.
enthalpy, right? So
Okay.
having
Okay.
higher enthalpy can be
Hmm.
can, maybe correlated with having a higher temperature. So this so if you have a higher temperature, so locally the speed of sound is uh, higher,
Higher.
and and the distance from the H naught to that point, H naught line
Hmm.
to that point is smaller. So so visually we can say, or maybe mathematically also we can prove that this the the velocity at that location is lower and speed of sound is
That
higher. So
location is
it's
higher.
in a
Okay.
subsound. It's subsonic
Great.
region.
Great. Great. Because at least in these 2 points, the top point will have definitely have a lower Mach number than the one with the point lower on it. Because velocity on the where speed of sound is also lower, right? So which will imply that Mach number has to be greater than Mach has to be greater on the lower point. Great, great, amazing. And one more thing that in the limit this in the limit Mach number goes to zero, we know that this can have inputs to this line, and only the top branch has that property. This branch does not have that property. So that is also one thing. Great. Okay. So now we are left with that shift with increase in G. Can we look at that? Why is that happening? Let me think about that as well. So let me think. Okay. So a higher G. Let's see if we can deal with it. Okay, yes. So look at it from this point. Okay, fine. Okay. So one way to look at it, there can be multiple ways to look at it, but uh, one way to look at this one is let me in here. Yeah. So no wait. Yeah. The easy way to see that is to let's see that. Okay, let's go for it. So what we'll do is we write the governing equation, see what okay. In constant area, the in why is it we have to use the moment continuity equation and energy equation to see this. Following which it implies that HS G square by 2 rho square is constant. Okay, and we'll write rho square as specific volume. Let's say this or yeah, let's say this as specific volume. G is a constant. Okay, G is a parameter. Again, G, you see that now we have our equation into state properties, right? So if I were to talk, if I were to draw a plot between H and B, H and yeah, B only, specifically, how would it look? How would it look? Yeah, what do you call the quadratic things under the
So
negative slope because
parabolic.
G yeah, parabolic. Sorry, not quadratic. Yeah, quadratic or parabolic. That's fine. Does it? Yeah. Let me draw this. Right. Something of this sort. Okay. Now what happens if we increase G? If you increase G, you are going to get these faster drops, right? If G decreases, what you're going to get is a so let me write this down. Fine. Okay. Mm, fine. So first of all, what is peak point gonna imply? The point at which rho is mu is zero. What does that imply? Well, that will be a singularity, isn't it? No, wait. Yeah, what will that? That won't be a singularity. So what is this peak point where this specific volume is zero? That will imply the static conditions. Because if rho is mu is zero, that implies u has to be zero mm, for g to be a finite value. So suppose a reservoir, okay, a reservoir, we consider, well, largely speaking, we can't just say that it will be the reservoir condition, but we know that asymptotically, this is where it should go. See, that is a singularity point because rho cannot be infinity. But loosely speaking, if we consider a reservoir with fixed mass, um, and uh, and it is a large reservoir, it is a very low velocity reservoir. It does not have any velocity, but it has a finite mass velocity. That can only happen if your density goes to zero, density goes to infinity while u goes to zero, right? So this is the line of ignition enthalpy, first of all. And what we see is, uh, okay, now let's also draw similar to how we drew isentropes. Sorry, isobars in that Mollier diagrams. Let's also draw isentropes in this curve. Okay, to see why a higher G implies a leftward shift in the Mollier diagram. See. Let's plot this TS, this isentropes. So again, similarly, I'm going to write as TDS equals to TH minus VDP. Can we draw this line? Okay, isentropes. There is another way to look at it. Isentropes. Uh, let's invoke ideal gas equation. We have been using ideal gas equation so far. So in ideal gas equation, we know PV to the power gamma, right? That is how isentropes are gonna look. Okay. How will these isentropes look, Pranav, on this H mu curve? We can actually see for ourselves. See, P equals to uh, T by uh, T by V. So you can simply write this.
EV raised to gamma minus 1.
Yeah. Now, how does this look like? What is this curve? Do we know the shape of this curve? X y
So
equals to k by x to the power some n. Yeah. Does it matter what this n is? Is n positive or negative? Does it matter?
uh, it would, if n is
Right.
negative, then we would get some polynomial.
Suppose n equals to 1.
Or,
N equals to 1. Then
so
how? Huh?
it would be a rectangular parabola. Sorry, hyperbola.
Yeah.
Uh,
Hyperbola. Great. So something of I would have to now use pen. I don't know how can I use these lines and all. Let me draw this. So it can look like a parabola. What happens now? Now, what if this n for air it will be zero point 0.4, some fraction less than 1, right? Less than 1. How
Yes,
would it look like?
it would be the value. Wait,
So what we can do is we can just numerically see what if x increases. Will x to the power zero point 0.4 increase? So let's first look at how uh, x and this thing looks like. Okay, let me just do that also. simple. I'm,
So
but
so
yeah.
the what can I visualize is that it would look like a rectangular hyperbola, just that the
Hmm.
the horizontal section, or what can I say, the section near the x-axis, that would be
Hmm.
a little bit thicker.
You mean
Like
it will be a little bit stretched?
no, not stretched, not stretched. What can yeah, I cannot say that in words actually.
Okay, let me see. Let me draw it
So
for you. Hmm.
it's
So it can be. Let's see.
what I mean to
Right.
say is
So
that
there
it's
can.
just that it will reach the same value of y at a higher
Ah.
value of x. I mean, think so.
Okay. So what we are doing is let's do it here. I think you're using the same approach as what. Let's see. So first, let's draw x to the power n. Okay, that's just too bad. Let me just give me a second. This is a little slow today. Go to a new page. Hmm. It's pretty easy only. It's straightforward, but just for the sake of understanding, because now that we are doing it, x to the power n. So just following what you said, what happens when x n equals to 1? N equals to 1 is simply a straight line, right?
Yes,
N greater
yes,
than 1 is something of this sort, and similarly, n less than 1 will be this thing, right? And less than 1. So this is what we are interested in. And if we were to plot minus, now it's basically k n minus, right? And this is 1 by, so y equals to k by something, right? K by a smaller value. We just reciprocate this thing. So just like how you said, it will be something of, again, parabola only. Uh, Too bad. But anyways, it will be a parabola. Let's use Desmos. Let's use Desmos. So that would be better. We have been using Desmos all session. Let's
yes.
use that.
It will reach infinity a little bit slower, I can say. Slower or
It will reach infinity faster.
faster. On
Sorry,
X,
this
I mean.
on x-axis, it will reach 0 comma infinity faster. Is that what you're saying?
No. Slower. So we
Lower.
get a
Okay.
fatter region near the x-axis. Yeah.
Okay. Understand exactly what you mean by fatter, but I understand that you're
Yeah, means a
thinking
thick
of.
a thick region in the direction of x-axis near the y.
Yeah, yeah.
Let's
Got
plot.
it.
Sorry.
Yeah, I'm able to at least see that you're able to make sense of it. So that's okay. Let's see. Let me share that screen. Today my this thing is giving headaches. Laptop. So x to the power n and x to the power m and x. So let's put 1.4, 1.5, and zero point 0.5. Yeah, I drew it incorrectly. Yeah, will not be like that earlier. So it has to have this thing because all three values will go to one, like will pass through 1 comma 1. Yeah.
It
So this
was
is okay.
y into x raised to y, right?
Yeah,
Like
yeah,
y
that's
in
true. I'll draw that. I'm just seeing how x to the power n goes, right?
okay, okay,
Now we'll see
fine.
how x to the power 1 minus n goes, just to get a feel of what is going on. So just like how you said, so this blue line corresponds to a n greater than 1, whereas uh, this m line corresponds to a value lesser than 1. So what we see is, roughly speaking, we are getting a, like, this curve is shifting or getting rotated, let's say, or I don't know how to say, like, how to imagine that. Anyways, now what we'll do is we'll see the graphs in the we'll see how this thing is, like, the final thing. Okay. Hmm. So blue line corresponds to the case of ours. We kind of see that it shifts upwards, or at a given x value, it will have a lower y, right? But it is still some sort of hyperbola. What we can also, like, now, this was not very important to the question itself, but what is more important is how it increases as this value increases. Okay. So a higher k will give you a higher shift. Okay. Okay. Now I'll go back, start again, share this screen. Right. So now we know that something of these sorts are going to happen. Let me see if I'm able to draw. Yeah, not very well, but anyways, does not matter much. Okay. Um, what else? Okay, fine. Now I am asking, this is S1 and this is S2. Which one is a higher isentrope? Which one has a higher isentropic, like this S1 value is higher or S2 value is higher? Let's see that also. Can you tell?
I think give me a moment.
So we can use this again, this TDS relation to get. Did you say something? I was not able to follow.
No, no, I just said give me a moment. I was
I'll give
trying to
you a
solve
moment.
it.
Yeah, yeah, go ahead. Go ahead. Think about it.
So
let me
I can
yeah.
going
So
nowhere.
what we can do is see this can be a little tricky, but not tricky. It, just like it's a trick, like it's a trick. But anyways, see, we saw that this constant value. See, T is related to H, right? So for a given, like this is something of this sort, H V to the power gamma minus 1. Oh, this one is pretty bad today. So H, let me just recite it. So we know that H V to the power gamma minus 1 is the curve equation of the curve. And we also saw that H1 V1 to the power gamma minus 1 equals to H2 V2 to the power gamma minus 2, right? Um, and we also saw that this curve increases, this curve moves upwards if we increase this constant value, right? So for a given t, so for a given t or given h, if we were to this is the equation. So this is, let's say this is h1. It's too bad. There is a lot of lag also. Suppose this point, there is some point on this isobar. If yeah, we can see it this way. See, um, hmm, we can see it this way. No, it does not matter. See, again, we will use this equation, okay? We'll have to use this equation because H equals to Cp. So TdS. Again, we are using ideal gas equation. So for a real gas, we'll have to see. But for an ideal gas, at least we can say these things. Du minus plus PdV. Now, again, now if we substitute and all those things, if we do along an isentrope, well, we can't use along an isentrope, no? Um, for a perfect gas, dH my dH, this is du, fine. Along an isen, okay. One more thing that we know is, let's say dH is a constant. dH is 0, which will imply du plus dPV. But that then we are going to just get that dDS equals to VT. That is what we are going to get. VDP. Mm, PV equals to RT. Enthalpy is a function of mm, I'm also forgetting how do we see this. Let me think. Go through this derivation. See, we will get delta S. Okay, it's gonna be CV ln T2 by T1 plus R ln P2 by V1. Okay, now we know from ideal gas equation that if the enthalpy is a constant, if we keep dH equals to 0, we know T2 equals to T1, right? In that case, we can actually write this down. Do you agree or am I making a mistake? Can we write this for a
We
thermally
can.
compressed ideal? Right? We can,
We,
right?
yeah, yeah,
So
it's
what we are seeing is that with an increase in specific volume, entropy is increasing. Do you agree? If H2 equals to H1, if H2 equals to H1 along this for a given y value, if we move in the direction of x-axis or in the direction of increasing specific volume, our entropy increases. That's the simple thing,
yes.
right? So S1 is greater than S2. We can just simply write that. Okay, fine. Now, how does that help us? One is not behaving. S1, yeah, S1 is greater than S2. Now, can you see why on an Mollier diagram, why a higher mass velocity will give you a shift towards left? See, we know G1 is greater than G2, right? This curve touches this isentrope earlier than this curve, right? It touches like this curve corresponds to a higher isentrope, like the tip of it, a point at which both these curves are tangent to each other. Let's say the first isentrope which touches it, the lowest isentrope which will touch it, will still be higher than G2, right? Does do you get my point, or should I clarify this? Let me clarify this. So how will I draw it? But let's try. So now we at least know that isentrope uh, rightwards is a higher isentrope, right? And on this H specific volume diagram, specific volume and enthalpy diagram. Now consider an isentrope which just touches this the first isentrope or wait, let me draw an isentrope which cuts both of these things, both of these curves, right? Something of this weird isentrope, right? S equals to 0, S equals to some S1. Oh, this is very hard, yeah. Yeah, S equals to S1. We see that G1 touches G2 before, like this has a higher length at a higher H values, and this one touches at a lower H values. Okay, so the corresponding delta H is lower for a higher mass velocity. Let's go back to that plot before. Okay, you draw an isentrope here that touches both of these things. Let me draw it here, or let me draw it using lines. You see, between G1 and G2, I have changed the order now. Don't get confused. On the previous page I used G1 was lower than G2. Don't get confused. Here G1 is greater than G2. you see that the corresponding delta H values are higher for a lower mass velocity, right? So G1 has to be greater than G2. That is the reason. Does this make sense?
Yes. Yes.
Okay. So yeah, you're saying something? No, I guess.
No, no, no.
Okay. So we can move ahead now. Next thing I thought, rather than doing a numerical, it's more of a derivation I had planned. So rather than doing a numerical, let's see if we can we can use we can I can generate a Fano curve for you to see how actually a Fano curve would look like if we use actual property tables and data. Okay, so I'll stop sharing and I'll open that uh, page where I'm going to plot that graph. Okay, fine. Give me a second. Let me set things up. Okay, so what are we going to do today is I'm gonna use Python to plot this graph. In Python, we have a lot of libraries. Well, not a lot of, but there is one library called CoolProp, which we can use to get property table data. So it is a lookup table only, but it's just they look it up for you. You push in the values, they give you the property. So and this is Jupyter Notebook. Not sure if you would know about this, but that is one good this is Python, right?
Yes.
You-
Yes, yes.
Yeah,
Yeah, I know.
you know about it, probably.
Yes.
So NumPy, yeah, NumPy is fine. Matplotlib. Have you used this extensively?
Not extensively. I had used this long time back.
Okay.
I don't remember.
Okay. What else? Okay. Then this NumPy is just a library. It's a very general library, but right now we are going to use it to save arrays and all, like lists. You think it about as lists, properties, and all those things. Matplotlib we will use it for plotting the data or the Fano curve, and then we are going to use this library called CoolProp and specifically uh, a special function from it called prop si. So it gives you the property in si form in si units. Now, okay, suppose this was your assignment, Pranav. Let's just interactively code. How would you generate? Let's say what all do you need to generate a Fano curve first of all?
Firstly, I need to set the T naught. Yeah, T naught.
So
T naught. I can.
why do we need stagnation quantities?
We
Well,
need
yeah,
to we need to set the H naught. So that
right,
we
H
need.
naught.
P naught.
So let's say we need to fix H naught. So stagnation quantities are important. Okay. So let's say we keep it at a high temperature of 350 degrees Celsius. 350 degrees Celsius. We'll also fix a stagnation pressure so that our bar or 100 kilopascal. So this units are in this one is 100 kilopascals and this one is 350 Celsius. What else do we need? Think yeah. So just using these properties, can we generate a Fano curve? So we will also need this mass velocity. Some mass velocity is needed because different mass velocities will give you different Fano curves. We just saw that. So let's just define it as 1 kg per meter square per second, 1 kg per second per meter square. Okay, let's just take some random value. What else? Okay, so first thing is let's say what are my stagnation density. Okay, so what we saw was before also we used um, continuity equation and momentum equation to generate that parabola. What we can do is generate that parabola, and from that parabola we'll generate the Fano curve. That is the easiest way to do things rather than bringing other properties into the picture, Mach number or anything of that sort. Let's just use we can also generate a Fano curve using a entropy value and different Mach numbers, but let's not do that. Let's use this what do you say that the parabola way of doing it. Okay, so let me generate the stagnation density there. So the way to do it is okay, we also need a fluid. Let me keep the fluid as working fluid as I'm going to use this carbon dioxide for just for some sake of it. um, So for this, how does this function work? This function works by putting the first key, this character is the property you need. D is for density and what properties you have. So we have temperature, so we'll give T naught, and we have pressure, so we will give P naught. And again, finally, the working fluid also is required. So this will give you rho naught. Let's see what is the stagnation density. So it gives you a value, okay, 0.849 SI units, kg per meter cube. Um, what else? Okay, okay. Now, given that stagnation conditions, how can we generate a Fano curve? See, in the asymptotic condition, acha, okay, in the asymptotic condition, as we saw, uh, density has to be very high for the flow to be near income, like near, um. So if you would remember said that here the density has to be very high. Okay, yeah, density has to be very high here in this part of it near the subsonic regime. Like we are incompressible regime, density will have to be like very high for the flow to like in near this regime. So to generate the curve very like in the asymptotic region, we need a very high density. On contrary, we need a very low density for the near the nose of it. Okay, so we are going to use different rho values to see how h and all those things varies. So let's say rho s is n p dot lens space. So now what I'm writing is it's a function, numpy function, which generates uh, if you give a range, it will generate a list between these two ranges. So rho into 5 or twice, let's say, and a low value of it, rho into zero point 0.1. And what else? Hmm. Yeah, you have to also give the number of points you need. So for a given rho s, now let's generate the other properties. So this is a for loop we are going to use as, and also we have also have to store the different properties in different arrays or different lists, so that we are going to do. So and enthalpy will store static enthalpy, we'll store, let's store mark number, let's store temperature, all those things we'll store. Temperature, right? Temperature is there. What else? Static pressure is there. Yes, yes, PS is needed. What else? We'll store okay, we can't store AS like this. We'll store speed of sound. What do you know what else we can store?
We can,
Let's say
you
P
can,
total S.
yeah.
What else? We'll see on the go. So HS dot append. So now append is basically adding something to the list, and the same function I'm going to use is just changing the. Uh, so wait. So it has to be H. So what is H? H is H naught. So we have to first also say H naught as a function, right? H naught as a value. Let's do that. Because we are going to need it to generate row like static enthalpy values can come from that. Wait, what happened? Everything is okay. So for the keyword for enthalpy is and this H capital H. So H naught minus G square by 2 rho square. The way you apply to the power, you put double star, double asterisk and multiply star. So that is okay. Now you have HS is there and you have row. So you have two properties, H and row, and you're gonna fill all other properties using these two state properties. Okay, let's do that. Keyword for entropy is S. We have this enthalpy and pressure. No, not pressure. We have density. So H and density, right? Now let's slowly build other things. So we can store temperature. Then we can also store speed of sound is also a property. Um, okay. Then static pressure is also a property that we have not stored yet. Um, so Pranav, I'll take a small break. I'll go use the washroom and come back. Okay.
Yeah, yes.
I'm back. Just give me a second. Okay. Okay. Pressure is there. Then we have MS. Okay. So we'll also store VS also. Let's store VS also. We just oh, hmm. So let me store or simply we'll store VS MS dot append. Right. Okay. So MS is this. So we know G divided by rho is U divided by AS minus 1. So AS minus 1 means the last element in this list of AS, which as we will keep appending or we will keep adding things into the list, the last element will be the recent element. So that is how we'll store it. So G by rho is U, U by A is MS. What about PTS? So PTS will be, we need a R value also for PTS. Or let's store delta S by R. R we know what is R for this. So for gas of this 188.9. For R is simply this value. And for that we'll need S naught also. So the formula we are going to use is ln, so PT2 by PT1 equals to e to the power delta S by R or minus delta S by R. Okay. Okay. So delta S. So basically delta S is S0 minus S1 or SS minus 1 by R, and this entire value will be ln. So you're going to use a numpy function for this, ln for ln, numpy log. So numpy log means ln, and then we have uh, e naught times this value. And let's see what we get. I don't think there is anything else for us to save. Let's see if we get it nicely. No, something is wrong. FOS row not. It should be row not. Auto objective not successful. Okay. think everything will be fine. Valid and quant. Spy. So we are not getting what exactly we were expecting. Let me see. There is some error. In this error. So this is one. Okay. 65. Ah, okay. Let me give a higher G value. We have given a very low G value. That is why maybe. So it just see if a G value is very low, it will give you a very incompressible fluid only, incompressible flow only. The G value should be high enough. Let's see. Hmm. So let's look at it. So we are getting something of the Fano curve. Okay. Go down to 0.15 and generate this again. Hmm. So we have to give a high enough H value also. That is also very important. So okay, now we can do one more thing here. We can see how with H, how with G, this Fano curve will move. Okay, that is something we will see. Uh, One is pretty slow today. what I'll do is first save this as a function. So now I'm making a function out of it so that we can give multiple g values or t naught or p naught value. So no p naught. What I'm doing is I'm giving some values to this function. You can s- go through these normal Python courses or stuff to see how exactly am I doing things. Okay, like what is the syntax and all. So there is one more issue which we need to resolve first. Let's resolve this issue. First of all, let's see how mark numbers are. Okay. Um, right. So we see some mark number values from 3 to very close to 0. Okay. And let's also see. And at a low row value, mark number is high. At a very high row value, mark number is very low. That is something that we would have expected. Mm, what about this? So I'm getting a negative value. P naught times log SS. Have I done it incorrectly? Maybe. That's not it. What is the error that I'm making? Let me just check. To the expression for. So, Pranav, if you're there, what is the expression for? Is this expression fine or is it wrong? I think it's fine only. It's e to the power, not log. It's e to the power,
I think
right? Yeah, exponential. This one is fine and will be S1, this one only. Yeah, you're there, right? You're saying something.
no, no, no. I'm not saying anything.
You understand this, right? I was making a small mistake
Yes,
there.
yes.
Is this? Now it's fine. Um, yeah. So good thing. Let's look at this. So make that will make things clear. Okay. See how PLT dot different. What we'll see is that at mark number equals to 1, wait, let me check. So P T by this thing. Yeah, it's minus delta S, I guess. So would be fine. So you see that the lowest stagnation temp this yeah the lowest total temperature pressure occurs at Mach number equals to 1, right? It occurs at Mach equals to 1 because
Yes.
reaching those sonic condition will result in the lowest pressure drop, lowest total pressure drop. So that is some, so this is all fine. uh, there is also one more thing that we should look at. Let me do that also. Plt dot plot ms plus np dot array. Just forget about these arrays and all. Plus actually should be rho s or what has not multiply. I have not found out u, right? Velocities I have not found out. Dot u square rho s. Let me also save us also. Why am I doing so is I'll tell you. We could do the same thing with air also. That is also fine. Let's see. We get something nice. No, this is US. Store it as US. US does not make any sense. There is no static velocity, but anyways, yeah. So this is PS by rho U square is okay. Hmm. Similar to how we saw that with the total pressure drop, the lowest value comes at sonic velocity. And what have I plotted? I have plotted P plus rho U square. Now P plus rho U square, if you would remember from Fano, the momentum equation for Fano line, it decreases as you move in the direction of flow. It decreases because of frictional effects, and it decreases by F delta X by D, half rho U square. Okay. Now, suppose I plot, if you would remember normal shock thing there, if I plot a such line, let's say some small value, zero point 0.9 or something, no, not 0.9, 0.09. Okay, yeah. So let me just also put color equals to C1. So this, whatever you're gonna see, the orange line, right? This orange line is kind of, let's say, zero point 0.7, 0.07, right? You see that this line is cutting um, the blue line and 2 points. What does these 2 points signify, Pranav? If you can just tell me quickly.
Uh,
These I've drawn.
see
Yeah,
the plot. What was this plot again? It was
yeah. Let me
the
let me
MS
let me
versus
let me write that down.
what's on the Y? Okay, Y.
Yeah. I'm writing it down. So it's actually this square. Is that something physical or come on, get plotted fast? Yeah. No, what's wrong? No. Okay. That is weird. There is nothing called as row. What do we call? That's row only, no? Um, okay, anyways, I'll just write it as P row U square. Let's forget this. P plus row into U square. Okay, let me just tell you that these 2 points corresponds to a normal shock. So see, along a normal shock, normal shock, if you think about it, is similar to what is uh, a normal is Fano line. You'll see that only along a Fano line, this P plus rho U square keeps on decreasing. Along a normal shock, P plus rho U square is a constant. So these 2 points, just using the Fano line itself, if we plot constant lines of P plus rho U square, we can find a normal shock solutions as well. That is what I wanted to just
So sorry.
show.
Sorry.
Yeah,
Can you repeat what changes and what remains constant?
yeah. So
You
let me
you
do that on this thing. Let me do this on here. See, along a normal, so what are our governing equations? These are the three governing equations we have, right? This is Fano flow, right? Do you see this?
yes yes.
Now just tell me the equations for a normal shock. What happens in a normal shock? What how will the governing equations change? We will not have this, right?
For ha we neglect that goes up.
That goes out. So if you see that P plus rho U square is remains constant along a normal shock, isn't it? No?
Yes.
Am I making a
Hmm.
mistake?
So you
Um, no, rho U is a constant.
constant.
Yeah. So wait. So dP is P that gets integrated. Rho U remains constant. Yeah, rho U square only. No,
It's
so rho U is a
it
constant. So
was
du
row
will become
into
du.
use square, I think.
Is a constant. So du will become U itself. dP will become P. So P plus rho U times U. So rho U square. No? What about now? G is a constant. How does integrate this equation? P plus GU, right? Remember you there? I don't know
Yeah.
if you're there.
Uh, I
You
am.
get
I am.
you're thinking. Fine. I'll wait.
This GB is you.
You can tell me where you're having issues. What is that is not like is not setting with you. Like what is not setting right with you? We're talking about a standing normal shock. think it's okay, right? No? Maybe let's go to the books. Let's go to the books. Let's just see once what book says, then might be better. Pranav, you are having an issue, right?
No, no, I was just jumbled in my thoughts.
Okay. Is there something you are still not like is still worried about, or you are
No, no,
having
not
issues?
worried.
I know, not worried. I meant you're still having some issues, some not something not setting right with you.
No, no, I have confused myself. I need to come out of.
Okay. Okay. See, these are the governing equations for a normal shock. What's the confusion? If you can just tell me, or we can work it out together. If you can tell me, you can be wrong. That's okay.
No, no, no. I cleared that.
You cleared it up.
Yeah, yeah.
Okay. So, anyways, I'll just move ahead. We don't have a lot of time now. So this is something that happens along a Fano line. There is always see, there is a sonic branch and there is a subsonic branch and there is a supersonic branch. This is what these branches are telling. This is telling you on this curve. You see that there is a subsonic branch, this branch, and there is a supersonic branch. For both of these branches, there will be a point along which p plus rho u square will remain a constant, and these 2 points will correspond to a normal shock conditions. So we can find out normal shocks on the Fano curve also if we plot it. Okay. I also wanted to show you guys how this Fano curves moves when we give different g values. So here I had done it already down on this thing. What I did was plot three Fano lines, g equals to 90, then g equals to 100, and g equals to 110. So the blue curve is the 91. Uh, Orange curve is g equals to 100, and g equals to 110 is the green curve. You see all these three curves, they move leftwards, something that we saw today, right? We can do other things also. We can plot what all? We can plot Mach numbers also. Let's try to plot Mach numbers for the sake of this, and we'll see something nice. So if we were to plot Mach numbers, let's see what happens. So we can do a lot of things if we want to plot it on ourselves. Then we can see what all goes, like what all happens. So if you will note, see near the nose, you will see a color corresponding to mark of 1. At top notch, the mark number is very close to 0. At downstairs, as you keep coming down on the supersonic line, mark number increases. But you can see near the near the nose, mark number is close to 1. It will actually be exactly 1. So we can see that also happening. Okay, then what else? Um, these are these are few things that you could do. Let me see if this what is wrong. Log scale. Okay, let's leave this. These are few things that you can do. You can also plot lines of static pressure. Let's see static pressure. So mark number. Let's see static pressure also. 1 by E6 basically means we are calculating pressures in um, megapascals. So you see. this value reaches a like it's reaching a top value of some value close to zero point 0.5, and here it is going down to 0. At again nose, it will be P star, and this orange value should correspond to P naught. What is our P naught? Let's see. P naught is 1 e to the power 5. That should be our static pressure also. This stagnation pressure, this pressure should also be equal to this thing. Uh, yeah, so probably it's still not reaching 1, it's zero point 0.5, um, because of because it is asymptotic. Only in the limit it will go to 1. So we'll have to decrease it even further if we want to see that. Let's say 15 or something. We're reaching a PS value of 1.4. That's not possible. Something is wrong with it, but ideally it should have come like approaching to P naught. Let me think about it. Right, P half M square. Yeah, yeah. It will approach 1E5. 1E5 is what? Point 0.1. Wait. It should be point 0.1. Why is it going so low? So high. This is 1E5. We can also plot PTS. I'll check why this one is coming higher than P naught. It should not. PTS is fine. So this is one way of doing things. I'll stop here. I just wanted to show how we can plot it, how it actually comes. Um, Next time also I had planned one small question. I'll see if next time we can continue that, or we'll start with the Rayleigh flows. So that's all for today. Let's meet next time. Thank you.
Yeah.
Bye.
Thank you, sir. Bye.
Thank you.